Hello again, and welcome to another fun-filled evening in math with Mr. Sims. Today we're going to be talking about recursive formulas and recursive functions, and so this should be a good old grand old time. Basically, this is going to be a basics video where I tell you how to read the notation, basically understand the language of what we're working with recursive formulas and recursive functions. So I'm hoping it's just going to be something that is really helpful for you, and let's get right into it. So basically, when we're talking about recursive formulas and recursive functions, there's two different ways that you can look at this. There's two different notations for it. When I grew up, I used this notation a lot. This one is another one that you'll see often as well. And basically, they both mean the same thing. They just look different. So just so you understand, this is using like f of x, and this is using a sub n and a sub n minus 1. And then this is another version of what you're seeing here, and I'll talk more about that in just a second. So basically, the whole point with this is you have f of x here. That f of x really, it just means any term at all. So if I had, if I had this one, this just means any term. Doesn't matter what the term is, just any term I'm looking for, right? Any term I'm looking for at all is basically equal to the previous term, right? The previous term and you're doing something with that previous term. With that previous term, you're either going to add something here, and that if you add something, that's going to make it a arithmetic sequence, okay? An arithmetic sequence. Sorry, excuse my handwriting here, but that's going to make an arithmetic sequence. If I am multiplying it by something right here, then that's going to make it a geometric sequence. All right? Geometric. So once again, if I want to find any term, it's basically my previous term either added to something if it's an arithmetic sequence, right? Or it's going to be multiplied by something if it's a geometric sequence. And that might not mean a lot to you right now whether it's arithmetic or geometric, but what it basically means is arithmetic, it's a sequence of numbers where you're adding the same amount each time. A geometric sequence, you're multiplying by the same amount each time, or dividing by as the case may be. Arithmetic, you might be subtracting. You might be adding a negative number, which would be akin to subtracting. And so basically, that's how this f of x notation works. Now, the nice thing is there's a whole other notation. This other notation uses a sub n, and it's the same exact thing. This, once again, is any term, and this is also any term. And this is going to be the previous term, right? And you'll notice the previous term because it's n minus 1. So if this is n, let's say this were 4, for instance, this would be a sub 3, the third term. So the previous term, whichever term came right before it, right? And then you're going to be either, once again, adding something to it if it's arithmetic, right? Or in this case here, you could be subtracting something from it. If it's, you could be adding or subtracting something if it's arithmetic. In this case here, you could be multiplying something by it. And if you're multiplying something by it, it would be geometric. Okay? Geometric. So once again, geometric, arithmetic, right? Arithmetic because it's adding something or subtracting something. If you're adding a negative, you're really just subtracting. If you're multiplying by anything, or dividing by anything, then it's going to be geometric. So anyway, that gives you the idea of kind of what we're going to be talking about a little bit. If that scares you, that notation right there, don't let it scare you. It's just, it looks complicated, but the more you do it, just the more you get used to that language, right? And so an example, just so you know, for the first one here, let's say I wanted to make an arithmetic sequence where I'm adding something. Maybe it's the same thing I'm adding each time. So 3, for instance, let's say I wanted to add plus 2 each time. Right? Then this one would be 5, right? And then the next one would be 7. And this is an example, once again, of an arithmetic sequence because each time I'm adding plus 2. and this would be a 9. So on and so forth, right? And I could really go on forever with this. That's the nice thing about sequences. Sequences continue on to infinity. And so this one here is a fun one. Now, if I wanted to write the notation for this now, like to actually go to my notation, I would say f of x is equal to f of x minus 1, right? Plus, now I have to get my plus 2 here. I'm adding plus 2 each time, so this is my pattern. My pattern is plus 2, so that plus 2 becomes this plus 2 that you see right here. And all that means is if I want to find any term, I just look at the previous term and add 2. So if I wanted to find the next term, let's say here, I'm going to look at the previous term and add 2. So if I want to find the next term, I look at this term here, which is my previous term, and I would add 2. Does that make sense? So hopefully that makes sense to you. If I wanted to write it with this notation here, I would write with a sub n is equal to a sub n minus 1, n minus 1 plus 2. And that right there is my recursive notation in the other notation, the recursive function in the other notation. Now, this is almost complete, but it's not quite complete because I'm missing a key part here. This sequence only works in the instance for, this is true, for f of 1 is equal to 3. In other words, this function no longer works. This notation no longer works if f of 1 is something different. For instance, let's say f of 1, instead of being 3, because f of 1, my first term, f of 1 is 3, therefore it works. But let's say my first term instead was, let's say f of 1 was in fact 2. Well, then my whole thing shifts. Instead of being this, it would no longer be this. Instead, it would be this. 2, 4, 6, and 8, right? Where each time I added, I'm still adding 2, right? Still adding 2 each time. But notice the whole thing's been shifted down 1 because I started my first term at 2 instead of 3. And so anyway, it's very important that you have that first term. This is true for a sub 1 is equal to, this is true if a sub 1 or for a sub 1 is equal to 3. That would make this one true, okay? So hopefully that made sense to you. I don't want to confuse you with this one. But basically the whole point is you need to have your notation, and this shows the pattern, right? And then you need to have as well your first term. You have to tell us what your first term is. Otherwise, like I said, your pattern will remain the same, but your whole sequence will be shifted up or down depending on where you started, right? So if I wanted to now do a geometric sequence, remember this was an example of an arithmetic. It was an arithmetic sequence because I added 2. This adding 2 is what made it arithmetic. So now let's move on to a geometric sequence. This is going to be a geometric sequence. I'll write that down here to be consistent. So geometric. And in my geometric sequence, I'm going to actually multiply it times something. So for instance, let's say I had, let's say let's start with a just regular number. Let's start with 4. And I'm going to go ahead and multiply this 4 by a 2. No, I already used 2. I'm going to multiply it times 5. So 4 times 5. And so if I'm going to multiply it times 5 there, the second number in the sequence, my first term is 4. My second term in the sequence is going to be 20. My third term in the sequence is going to be 20 times 5 would be 100. And my next one would be 500, and I'm just going to put dot, 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 because at this point I could just keep going forever. And so once again, this is, if I were to write my notations for it, this would be f of x is equal to f of x minus 1 times 5, right? Now I can put the, I shouldn't use that times 5, times 5. Now honestly, most times you're not going to see the times 5 there. Instead, what you're going to do is you're actually going to see them put it first. And so I'm actually going to go back here and change that. I don't like the way I did that. So 5 times f of x minus 1. All right. The next one is going to be a sub n is equal to 5. If I was writing it the other way, it'd be 5 times a sub n minus 1, right? There we go. And that right there is my, these right there are my two notations for it, but I am missing something key, and as you guessed, you probably guessed that I need to indicate what my first term is, and this is true if, or for, the instance where f of 1, this is if f of 1 is equal to 4. And I'm using these interchangeably, the for, the if, because you can see it lots of different ways. So if f of 1 is equal to 4, and this one's going to be for a sub 1, right? For a sub 1 is equal to 4, right? So that would be my answer if I had it in this notation, and my answer in the other notation would be this if they were asking me for the recursive function. So once again, this is arithmetic because you add it. This one here would be geometric because you're multiplying by 5 each time. All right. So okay, I'm hoping that that made a lot of sense to you. We're actually going to jump into some examples where we can just try and figure out what the formulas are. All right. So let's go ahead and take my pen here. Well, let's go over to this one. So here's our first example. We have 37 to 67 to 97 to 127 to 157. So when I just look at a series of numbers, I have a problem. What I have to do is I have to figure out, well, first of all, are they adding to get the next term, or are they multiplying to get the next term? And so I'm looking at this here and I'm thinking to myself, all right, well, I always like to start with addition because addition is just easier in general. So to get from 37 to 67, it looks to me like I'm adding 30. But just doing it on one term doesn't tell me anything. What I need to do is I need to check, does it work for the next term? So the nice thing is I'm going to do it for the next term too. Is the pattern add 30 between 67 and 97? And the answer is yes, it is still add 30. Okay, so the good news is each of these just seem to be adding 30. So that's good news for us. So what we're going to do is I'm going to take now and I'm going to write my function for this, my recursive function for this. So to write my recursive function for this, remember I start with f of x. Any term that I want to find is going to be equal to my previous term, f of x minus 1, plus, it looks like plus 30. And that right there is my recursive function for this, except I need to write the specific instance that this works. And that's only true if f of 1 is equal to 37, right? All right, so my next one, if I want to do it with the other notation now, this isn't, I don't want that to look like a division bar, so this is one answer here. If I wanted to do it with the other notation, I would say a sub n is equal to a sub n minus 1 plus 30. And once again, you'll see that same plus 30. You'll see the same x minus 1 or n minus 1 or whatever, right? Like you'll see it. It just looks a little bit different. And this is true for the instance where a sub 1 is equal to 37, and only that instance. If you try and make it a different number, it'll actually change your sequence. So, all right. Hopefully this is making sense so far. I hope this is not too cumbersome on you. All right, so that's our first example. Let's go ahead and move on to my next example. In this one here, it's -3 to -6 to -12. So now we're working some negatives that can look a little scary at first, but don't let it scare you. Basically, what you're looking at for this is you're looking at an instance where it looks like each time I'm going to try first of all adding. So if I were to do this here, I would be adding -3 each time, right? But the thing about adding -3 each time is it works for the first one, but if I try it on the second one, if I had -3, that's actually going to give me -9. and negative 12 is not the same as negative 9. So that tells me that this negative 3, adding negative 3, is the incorrect option. So now I have to put my thinking cap on and say, all right, it might not be adding then. It's probably instead a geometric sequence where it's going to be multiplying times something. So what would I multiply times negative 3 to get negative 6? Well, the answer is I would multiply by 2. So in this case here, I'm going to multiply by 2. And I'm going to multiply again by 2, and it does work. Negative 6 times 2 is a negative 12. Negative 12 times 2 is a negative 24. So I think I found my pattern here. It looks like it's multiplied times 2 each time. Now, just so you know, you always want to check at least 2. I would always suggest checking 3 just to make sure that you haven't made any serious miscalculation. But if you just check 1, you don't know if it's actually multiplication or addition. At that point, it could be either. So you need to check at least 2. I prefer checking 3, and I would suggest you do the same. So anyway, in this case here, I have negative 3, negative 6, negative 12, negative 24, and negative 48. Looks like they're being multiplied times 2 each time. So I'm going to start this time with the a sub n. And at this point here, I want you to pause the video and try and write the notations yourself. Hopefully you did pause the video. As I always say, if you are not actually actively working the problems, you're really kind of wasting your time, because you need the practice, you need the actual, you need to help your brain commit it to memory, and the only way they do that is by actually doing the problem. So if you don't have a piece of paper or pen handy right now, just pause the video, go grab a piece of paper and a pencil so that you can make sure that you're actually going to really learn the stuff. No, seriously, go do it. All right, hopefully you did. Without further ado, let me move on. So in this case here, it's times 2 each time, right? So I'm going to take my a, and if I want to find any term of a sub n, it's going to basically be equal to my previous term, a sub n minus 1, and I'm going to multiply times that previous term, this 2. So it really is 2 times a sub n minus 1. That looks like a 29. I don't like the way I wrote that. Let me do that again. Is equal to 2 times, right, a, and sometimes you won't even see that multiplication symbol, so I'm just going to leave it off this time. 2 times a sub n minus 1. And that would be my final answer. All right, hopefully this is making sense, and this is once again for a specific scenario, and it's for the scenario where a sub 1 is equal to negative 3, okay? So that's your first scenario, your first recursive formula. Let's go ahead and move it to doing it the other way. It'd be f of x is equal to 2 times f of x minus 1, right? And this is once again for a specific scenario. For this scenario when f of 1 is equal to negative 3. And that right there, would be my answer for this if they wanted me to find the recursive function for this sequence here. And once again, this sequence, in case we're wondering, this sequence would be a geometric sequence. And once again, it's a geometric sequence because, that is horrible. Let me try that again. It's a geometric sequence because we're multiplying each time in order to get my pattern. So once again, this is the pattern here. This is the pattern here, and we're multiplying each time to get the next number in the sequence. All right, so let's go ahead and move on to the next problem. I think I can find one down here for us. Yeah. Here we go. So this is the next one, and you'll notice there's something really weird about what's happening here. This pattern here is starts off with a negative number, then it goes positive, then it goes negative, then it goes positive, and then it goes negative. I want you to just take a moment to consider this and think about it, and then see if you can figure out what the notation for this would be. Go ahead and pause the video and try it now. All right, hopefully you did pause the video, and I hope you really were successful in getting this. So what you have right here is you have going from a negative to a positive, from a negative to a positive, and so on and so forth, and I will continue that pattern. So that automatically tells us some really cool things. First of all, that tells us automatically that this is geometric, because a geometric sequence is going to be one where you're multiplying times something. And the way you get this pattern here is you get it by multiplying by a negative number. So the first time you multiply by the negative number, it's going to become positive, because the negative, it starts with a negative, so the negative times the negative makes it a positive. But then when I multiply times the negative again, it gives me a negative. Then I multiply times the negative again, the negative times the negative also again makes it a positive, and then the positive multiplied times the negative again makes it a negative. So basically I'm multiplying by some negative number. I just got to figure out what that negative number is. So what I'm going to do is I'm going to look at my pattern. What do I multiply time from -1 to get 6? And it looks like I would multiply times -6. If you said 6, that's not bad, except for the fact that this is negative. So a negative times a negative has to become a positive. So I'm multiplying times a -6, right? So that looks like x minus 6, but you get the idea. So this one here, I'm multiplying times, once again, the -6, right? I'm multiplying once again times a -6, right? And as you can see, it's the same pattern over and over, me multiplying times a -6. So in this case here, if I have -1 times a -6, I'm sorry, I already know that's the pattern. So now what I have to do is just make my notation. I'm going to start with f of x this time. I highly encourage you to write in both notations to make sure you get it right, right? So in this case here, it's going to be -6 times, times f of x minus 1. And that's very important. -6 times f of x minus 1. And that's for a very specific scenario. That's for the scenario where f of 1 is equal to -1. And that's my recursive formula for it, okay? I'm going to go ahead and also write the a one real quick. So a sub n is equal to -6 times a sub n minus 1, right? So hopefully that made sense to you. I'm going to get that a little bit bigger. Okay. And this, once again, is for the scenario where a sub 1 is equal to -6. No, I'm sorry, not -6. For the scenario where a sub 1 is equal to -1. Thank you. So, all right, there we go. That's our two recursive functions for this. All right, let's go ahead and move on to the next one. Ding, 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 ding. All right, so for this one here, we have a whole bunch of negative numbers in a row, and notice we don't have the negative to a positive, negative to a positive, negative to a positive, so on and so forth. So that tells me right there that I'm not multiplying by a negative number. That's good. I am looking at this though, and I'm going from -2 to -10. And the question is, how do I get from -2 to -10? Well, there's two ways. I could add a -8, right? Or I could multiply by 5. And the problem is I don't know which one is the correct answer at this point. So I have to look at my next term. To get from -10 to -5, I would multiply times 5, not add the -8. Adding a -8 doesn't get me there. It would get me to -18. So this -8 is not the right answer. It's in fact this times 5, right? So each of these looks like they are in fact times 5. And you could always, like I said, check 3. I would highly suggest checking 3. I just checked them all, no problem. And so in this case here, I'm going to start off with my f of x this time. So f of x is equal to 5 times f of x, sorry, didn't mean to put that other parentheses, 5 times f of x minus 1. And this is true if f of 1 is equal to -2. Okay? So all of this is true if f of 1 equals -2. All right, so hopefully that made sense to you. Hopefully that was good. If I wanted to do this in the other notation really fast, I'll do it. You get a sub n is equal to 5 times a sub n minus 1, right? And that's if if a sub 1 is equal to negative 2. Alright, so hopefully this is making a lot more sense to you now as we go. Let's go ahead and do another example. You'll notice this one's a little bit different than the other ones because you have 33, 29, 25, 21. It seems to be getting lower as opposed to bigger. So if I was looking at this one here, first of all, let me just realize that my first term in the sequence is 33, right? And so I'm going to go ahead and figure out, am I multiplying or am I adding, right? So it looks like to get from 33 to 29, I'm going to try adding first because like I said, it's easier. So it looks to me like I'm adding a negative 4 or I'm subtracting 4, right? And it looks to me here like I'm also once again subtracting 4. So the nice thing is this one actually works out pretty easily, where this is an arithmetic sequence. Once again, it's arithmetic because I am adding something each time. In this case, I'm adding a negative 4, so also known as just subtracting 4. So I have my function here. It's going to be f of x is equal to f f of x minus 1, and all of that is being subtracted by 4. So f of x is equal to f of x minus 1 minus 4. And if I just continue on and on and on with that sequence, you know, this function will help me get there. So just remember each one is a negative 4 because of this negative 4 up here, right? So there's that, and then there's also, of course, the a sub n is equal to a sub n minus 1 minus 4. This is the other way of writing it. So this is true for, this is if a sub 1 is equal to, this should have been if here, sorry. If a sub 1 is equal to 33. Once again, if a sub 1 is not equal to 33, the whole sequence will shift. So we can look at that a different day. All right, I got a few more examples for us to do. Then after I do those few more examples with you, I'm going to give a challenge problem. There is one that's a little bit of a challenge. It's not too bad, but you do have to think a little bit. So here's a negative 23rd, a negative 17, a negative 11, and a negative 5. So to get from negative 23 to negative 17, it looks like I'm doing what? Well, if you said I'm subtracting 6, you are almost right, but I'm actually not subtracting 6 because notice this is a negative 23 and this is a negative 17. So really, to go from negative 23 to negative 17, I'm actually adding 6. So my pattern is add 6. And my pattern is add 6. Okay? All right, so my pattern is add 6. And I'm going to take my f of x is equal to f of x minus 1 plus 6. And that's if my f1 is equal to negative 23. Okay. Once again, if I was doing that with the a sub n notation, it would look like this. A sub n is equal to a sub n minus 1. Whoops. A sub n minus 1, all adding to that 6. And that's if a sub 1 is equal to negative 23. All right, so hopefully this is making perfect sense now. We have 3 more example problems, like I said, then we have the hard one. But I'm hoping you're really getting the hang of this now. Like I said, this is just the basics of it. In another video, I'll try and do more complicated stuff like finding specific terms and things like that. But in this case here, I have 3, -9, 27, 8, -81, and you'll notice the same pattern of going from a positive, right, to a negative, to a positive, to a negative, and so on and so forth. This tells me I already know I'm multiplying by a negative. So if I multiply by a negative and my first term is 3, I'm going to be starting off by multiplying by, to get from 3 to -9, it looks like I have to multiply by a -3. And from -9, -27, it looks like I also, once again, have to multiply by a -3. Okay, so in this case here, I'm going to start off with a notation. So a sub n is equal to 3, -3 times a sub n minus 1, and that's my answer if a sub 1 is equal to 3. And that is my final answer for that. If I wanted to do it with f of x, then it would look like this. It would look like f of x is equal to f of x minus, -3 times f of x minus 1, all, not all over. And that's true for the scenario where f of 1 is equal to 3. Okay? All right, hopefully that's making perfect sense to you. Let's go ahead and do another one. Coming down to the last ones here. So this one here, we have the actual thing that we've been making, and what they want us to do now, let's say they want us to find the first 5 terms. All right, it could be a lot of different things, but they want us to find the first 5. Well, they give us the first term here. They say the first term is a sub 1 is equal to 2. So I'm going to start off with my 2. This is my a, once again, a sub 1. So I need to find out my a sub 2. If they want me to, let's say they said find the first 5 terms in the series, right? The first 5 terms. So if they want me to find the first 5 terms, I've got to start off with my first term, and I've got to look at the pattern. What is the pattern in this case? And it looks like to me like the pattern is this multiply times 5. Now they put their 5 in the back, but it doesn't matter. It's being multiplied times 5. So it doesn't matter if it's in the back or front. So in this case here, I have my 2 that I'm going to multiply times 5. 2 times 5 is 10. Yeah. Now I'm going to take that and I'm going to multiply it again times 5, which is 50. I'm going to take it again. I'm going to multiply it times 5 once again. And I get 250, right? And then I'm going to multiply it times 5 yet again. That should be a times 5. And 250 times 5 is going to be 1,250. All right, and once again, this is A1, A2, A3, A4, and A5. So these are my first 5 terms in the series or in the sequence. So this is my answer right here. Okay. If I want to make it pretty, I'd just have the 2, 10, 50, 250, and so on and so forth, right? So if I were to do this, no, that's it. I just do it like that. We're good. All right, let's go ahead and try another one. Ooh, look at this one here. So notice that this one, the first term is a -3. Notice once again we're multiplying, so because we're multiplying, I know that I'm going to multiply by -3 each time. So -3 times a -3 is, hopefully you said +9, because you're multiplying once again times a -3, right? So you get a +9. And then 9 times a negative 3, right? If I continue going, times a negative 3. 9 times a negative 3 is a negative 27, right? And if I want, once again, I'm looking for 5 terms, the first 5 terms in the series, right? So if I'm looking for the first 5 terms, I need to multiply times negative 3 again. And I get negative 27 times negative 3, and I actually don't remember that off the bat of my head. Negative 27 times negative 3 is going to give me a positive 81. Actually, I should have known that. So I have a positive 81. And then I'm going to do one more where I multiply it times negative 3. And that's going to give me negative 243. Yeah, and so that right there is would be the first 5 terms in the series. Once again, this is my a sub 1, my a sub 2, my a sub 3, my a sub 4, and my a sub 5. Okay. All right, hopefully that's making perfect sense. Let's go on and move on now. Are we on? I think we might be on to our final problem of the night, and that's our challenge problem here. So we've had a lot of fun already, but let's go ahead and try our challenge problem, because our challenge problem has some fun stuff. So I'm going to look at this challenge problem now, and remember, I'm trying to find something that adds or multiplies to get me the next number of the sequence. So I'm thinking to myself, what adds to get me from 1/4 to 1/6? So let me think here. If it's from 1/4 to 1/6, right? These two have in common, let's see. In other words, let's say I have 1/4 here, right? Let's say 1/4. And I made it all the way to 1/6, right? If I made it to 1/6 and I was adding, right, then I'm looking at, let's see, 1/6 would be look something like this, right? Anyway, you get the idea. Basically 1, 2, 3, 4, 5, and 6. So to get from 1/4 to 1/6, it looks like I would have to add something, and we have to figure out what it is that we're adding. Well, in order to do that, I would need to find a common denominator, and then I'd have to subtract the 1/6 by the 1/4. And I could do that. I could absolutely 100% do that. But you know what? With fractions, I find it easier to actually look at the multiplication first. With the other numbers, we were looking at the addition and subtraction first. But with fractions, generally speaking, it's easier, I think, to look at the multiplication first. So what I'm going to do is I'm actually going to take my calculator. I'm going to take my 1/6 here, and I'm going to divide it by this negative 1/4, because I want to see what did they multiply to get me this negative 1/6. And if you actually go ahead and type that into your calculator, you get you should get 2/3, that you're multiplying times 2/3 each time. And what that looks like is this. If I'm multiplying times 2/3 each time, that would make sense, because I start off with my negative 1/4, right? If I multiply that times 2/3, that's going to give me 2/12. And you might be thinking to yourself, well, Mr. Sims, that doesn't look like that at all. But it does if you actually have a moment to simplify, because if I divide both the top and the bottom by 2, I get negative 1/6, which is what I got. So what made this a little more difficult was they simplified the fractions for you, which they're going to do if you see a term, a sequence with fractions, all right? So anyway, once again, all it was multiplying times 2/3. And I got that because I typed in my calculator negative 1/6, and I typed it in divided by negative 1/4. And by doing that, I was able to see what did they multiply by, and so I got 2/3 here. All right, so let's go ahead now and see if it works for the next one. So if you type in your calculator negative 1/9 divided by negative 1/6, you should also get, once again, 2/3. Okay, and if you want me to actually try that out, I have my negative 1/6. I'm going to multiply it times 2/3, right? Times 2/3, right? Let me just make a nice big dot there. And 2 times 1 is equal to 2, and 3 times 6 is equal to 18. So I have negative 2 over 18, which when I simplify becomes negative 1/9, right? So this is negatives, right? So negative 1/9, which is my next term. So as you can see, the pattern does seem to be times 2/3 each time. So because it's multiplying times 2/3 each time, I'm actually going to take now and make my recursive function. I know it's geometric because once again, I am multiplying by something. And so I get f of x is equal to 2/3 f of x minus 1. And this is for the specific scenario where f of 1 is equal to negative 1/4. And this right here is my way to write it with the f of x notation. If I wanted to use the a sub n notation, I would get a sub n is equal to 2/3 a sub n minus 1. And that's for the specific scenario where a sub 1 is equal to negative 1/4. Well, all right, I hope that has made a lot of sense for you tonight. I hope that this is starting to clear the language up for you and that you're understanding this a lot more. I don't think I have any more examples for you. No, I don't. Let's just go ahead and recap what we learned. So we learned at the beginning that there's two different notations for writing recursive formulas. There's the f of x notation that you see here, and there's the a sub n notation. And it's really just a matter of preference for which one. There might be benefits to both of them, but I'm not sure exactly what they all are off the top of my head. But anyway, you'll notice f of x is any term that you want to find is equal to my f of x minus 1. In other words, the previous term, either plus something or multiplied times something. Plus something if you want it to be arithmetic, and you're multiplying times something if you want it to be geometric. Oh, by the way, just in case you're wondering why I use these stars mean multiplication. Unfortunately, my computer doesn't have a good dot for multiplication when I'm writing like a term with the text box. So as a result, I had to use the star to indicate multiplication. Okay. So anyway, here's the a sub n is equal to a sub n minus 1 plus c and a sub n. So anyway, this is once again arithmetic because it's adding, and this is geometric because this is multiplying. So anyway, we learned about those. We learned about how they're made based on that, and how to write the notation where the pattern is. The pattern is located here or here, depending on what the type of problem is, right? And then we went and we did some problems, and we noticed that there are certain problems that are actually pretty cool because they will oscillate rather, between the -1 to the 6. So you have them oscillating between negative and positive terms, and that's pretty cool actually. So that if that is the case, you always know it's being multiplied by some type of negative number to get that. And then we just did some examples, and finally we ended, when all was said and done, we ended with this specific scenario where you had fractions and you had to figure out how to deal with fractions. Once again, I said with fractions, rather than trying to add to see what you're adding to each fraction, I would always do multiplication first to see if you're multiplying by something with fractions, because that's just going to be a little bit easier to deal with fractions, so you don't have to find common denominators and things like that. So anyway, I hope this made a lot of sense to you tonight. I hope you're having a lot of fun. Generally speaking, I think you guys are just amazing kids. You guys are work really hard. If you are watching this video right now, I just want to commend you on taking the time to just be more awesome, right? So here's a chicken just for your efforts. Here's a cute little chicken. Look at him, a mohawk. Yeah. He's got a mohawk. Okay, so here's Mr. Chicken, and that's just a chicken for you. Anyway, I hope you had a great time. I look forward, as always, to just having a great day with you. This chicken's saying bye to you. So, I hope that you learned a lot, and I hope, as always, that you're just enjoying math. Because really, I want you to reach the point someday where you just actually like math. And when you like math, you just have a lot more fun with it in general. Math is everywhere. You can always use math wherever you go, and just basically have fun doing it. And someday I hope you pass on that love of math to your kids as well. So anyway, I hope you're having a great day. Once again, I commend you for just all of your effort and all your hard work. I wish you the very best. Good luck on any test coming up, and I'll see you soon.